Okay, so welcome back from the coffee break. It's my pleasure to introduce the last speaker of the day, Yaron Ostrover from Tel Aviv University, who is going to talk to us about the Toda lattice and symplectic balls.
Thank you very much. So first, I would like to thank the organizers for organizing this beautiful conference and for the invitation to speak here. It's really a great pleasure. I'm going to talk about joint work with Vinicius Ramos and Daniel Sepe. And before I start, I would like to say, please feel free to stop me at any point if you have any questions or comments about what I'm going to say. So let me start with the general plan for the talk. In a sense, my goal is to explain the relation between four seemingly unrelated objects. So these are the objects. So the first one is the special convex polytope known as the rhombic dodecahedron. It has interesting both geometric and combinatorial properties. For some reason, I couldn't trace it back to the ancient Greeks. Apparently, during the Roman times, there were like dice games shaped like the rhombic dodecahedron. So I don't know if the Roman used it for gambling or did they play D&D, but anyway, it exists. The first reference that I could find is in one of the works by Kepler, where he used this convex polytope in one of his models of the solar system. So that's player number one, the rhombic dodecahedron. The second object is what we call Minkowski billiards. And I will say more about Minkowski billiards later on in the talk. But the general idea is that, well, think about Euclidean billiards, so where we have the usual law of reflection. But now the idea is that we play billiard in a homogeneous but non-isotropic medium. So in other words, we don't use the usual length functional to control the reflection law. We use a different length functional to define the reflection law. And in this particular case of Minkowski billiard, the geometry that governs the motion comes from a certain norm. So in the setting of Minkowski billiards, we usually have two convex domains. One of them plays the role of the billiard table, and the other convex domain controls the geometry with respect to which we play billiard. So convex domain, at least centrally symmetric convex domains, are in one-to-one correspondence with norms. And this norm, or the length that is induced by this norm, is the length that we use to define the reflection law of the billiard dynamics. So roughly speaking, these are Minkowski billiards. The next object in the talk is a famous completely integrable dynamical system known as the Toda lattice model. So you can see here the corresponding Hamiltonian function. This is one of the, in a sense, one of the first examples of completely integrable nonlinear Hamiltonian dynamical system. And the last object in this talk are symplectic balls, so symplectic images of the Euclidean ball. So what I would like to do today is to explain the relation between these four objects. That's the main goal of this talk. Okay. And I'm going to start actually with symplectic balls, so with the last one. Okay, so here is the kind of the general question. What can we say about the symplectic image of the ball? And in a sense, it's a transcendental question. I mean, we are very far from being able to give remotely close to something remotely close to a full answer to this question. In a sense, I guess it goes back to Gromov, to the non-squeezing theorem, maybe before. But in the non-squeezing theorem, we see these kind of obstructions of what can be done or what cannot be done with the symplectic image of the Euclidean ball. And I would like to mention two different motivations for this particular question. So the first one is the symplectic packing question. So what is the symplectic packing problem? So think about the Euclidean case. You have a ball, and you want to pack, let's say, smaller balls of the same radius inside the ball. So here on the left-hand side, you see kind of an illustration of the Euclidean case. Now, in the symplectic setting, the situation is very different in some sense than in the Euclidean case. On the right-hand side here, you can see a table with the percentage of the volume of the four-dimensional Euclidean ball filled by k smaller symplectic balls. And you can see, for example, that starting with 9 balls, there are no more obstructions. So you can always completely fill the Euclidean ball symplectically with smaller balls. But on the other hand, starting with k equals to 10, we don't know how to do it. I mean, there is no kind of a concrete construction of how to exactly to symplectically embed 10 balls fully inside the four-dimensional ball. So there is kind of a non-constructive proof that it is possible, but no one knows how to do that. So gaining information about, or one motivation to why do we want to study symplectic images of the Euclidean ball has to do with the symplectic packing problem. And for those of you kind of on the symplectic side of this conference, you probably saw these two pictures before, and I will go back to these pictures later on in the talk. But here you can see the symplectic packing of the ball with 4 and 6 balls. But I will go back and explain this picture later on in my talk. OK, so this is motivation number 1. And motivation number 2 is this famous question or conjecture by Viterbo, which is known as the volume capacity conjecture, an isoparametric type conjecture about convex domains. And according to the conjecture, symplectic balls should be the one that maximize the so-called symplectic systole. So this notion was mentioned in this morning, but let me just repeat the definition. We have a convex domain. Let's say we look at characteristic foliation along the boundary. There is always going to be a closed characteristic. We measure either the period or the symplectic action. It's the same thing for convex domain. And we take the minimal one. So the symplectic systole is the shortest, in the symplectic sense, closed periodic orbit on the boundary with some volume normalization. Okay. Now, in this week, you will hear more about Viterbo's conjecture, so I'm not going to say anything more about that. But this is definitely one of the motivations to try to understand symplectic images of the Euclidean ball. There are other motivations. OK. Let me show you now some pictures of symplectic balls in disguise, so kind of domains that are symplectically balls, but they don't look like that. And at this point, I should be a little bit careful, again, for the expert in symplectic geometry. There is a delicate point here by what do you exactly mean by a symplectic ball? Do you mean that the interior is symplectomorphic to the interior? Do you mean that you can find a symplectic embedding, maybe up to some epsilon? And OK, this is indeed a point that one should be careful about. But for the purpose of this talk, and I'm sorry if I upset the symplectic people, I'm going to completely ignore this little technical point. Okay, so symplectic ball, it is what it is. Okay, so okay. So here is the first example. Let's take R2n in classical phase space. And I'm going to consider the usual splitting to the kind of the configuration space, to the q coordinates and p coordinates with the standard symplectic form. And the domains that I want to consider in this talk are domains that respect this particular splitting. And I'm going to refer to them as Lagrangian products. Okay, so I'm going to take a domain in the Q space and another domain in the P space. These are the configurations that I want to consider. And here is the first example. So if you take the cube times the simplex, then this is a symplectic ball. And it is not super hard to prove. For example, if you are familiar with action angle coordinates and the Arnold-Liouville theorem, then this is essentially the image of the ball with these action angle coordinates. It's just a cube times a simplex. So this is the first example of a symplectic image of the ball that was known for a long time. A somehow related example is the cube times the cross polytope. So the dual, the convex dual of the cube, or if you wish, the unit ball of the L1 on the L1 norm. So this configuration is also known by somehow slightly different method to be a symplectic ball. And it is also closely related with some interesting conjecture from convex geometry, which is known as Muller conjecture. But this is not the topic of my talk today, but if you're curious about this relation, please come and we can discuss this after the talk. So for a long time, these were the only, or essentially only, two examples that we knew about for symplectic balls in disguise. Of course, there are some linear symplectic transformations that one can apply, but in a sense, these were the only two examples. Then, I think in 2015, Alexei Belitsky, who is here, proved a beautiful result. He considered the configuration of a simplex, again, with respect to this splitting of RnQ and RnP. So the configuration he considered is the simplex times another very special convex polytope, which is the permutahedron. And what he proved, and this is true in any dimension, that this particular configuration has the same symplectic systole as the Euclidean ball. So it should be a Euclidean ball, or a symplectic, it should be a symplectic ball. And in fact, there are some other reasons that support the conjecture that this should be a symplectic ball. But we still don't know. We don't know the answer to this question, starting with n equals to 3. Okay, so this is still an open question. So let me show you one last example, which is actually not of this product configuration, but I really, really like the example, and I couldn't resist the temptation to show it to you. And this is this strange object. It's the so-called 24 cell. It's a very unique 4-dimensional polytope. It's self-dual, reflexive polytope. And again, due to a result by Chaides and Hutchings, this polytope has the same symplectic systole as the ball. And we don't know if it is a symplectic ball or not. Okay. Any questions, by the way, up to this point? Okay. So kind of the starting point of our work, in a sense, was to try to answer this question. So is the Lagrangian product of a simplex and the permutahedron is a symplectic ball? So now there are kind of good news and bad news. The bad news is that we couldn't. I mean, we still don't know whether this configuration is a symplectic ball. But the good news is that we came up with a new kind of configuration, which is symplectically equivalent to a ball. So let me be slightly more precise. So this is the statement. If we take the Lagrangian product, again, in any dimension of the simplex and the rhombic dodecahedron or the n-dimensional rhombic dodecahedron or the generalized rhombic dodecahedron, no matter how you want to call it, then this configuration, not only that it has the same systole as the ball, it is a symplectic ball. Okay, so it's kind of a new example of a symplectic ball.
What's the Lagrangian product?
Sorry?
What's the Lagrangian product?
Oh, Lagrangian product, thank you. Let me go back. I'm sorry. Let me go back. How do I go back? So for me, a Lagrangian product is any configuration that respects this particular splitting. So you just take, say, a convex domain or a domain in the Q space, then another domain in the P space.
And again, just to make sure, so by something symplectic ball, you mean it's an image of a symplectic ball with respect to the moment?
Okay. So in this okay, let me see if I can find the statement again. How do I go back? Okay, so to be 100% precise here, let me say that starting with dimension 6, it's slightly weaker statement. It means that up to an epsilon, you can symplectically embed a ball inside, and again, symplectically embed this configuration up to epsilon inside a ball. So this is what I mean by symplectically equivalent. In dimension 4, we have some other tools that can give you a stronger statement about like really that the interior would be symplectomorphic to the interior. We can say something slightly stronger. But kind of the general statement is slightly weaker. But maybe I should say that, again, I apologize for going back in my slides, but if you think about these two motivations, the symplectic packing questions or Viterbo's inequality, it doesn't really matter which notion of or what is the exact definition that you use for a symplectic ball. It's essentially the same thing for these particular applications. And in fact, I don't know any application or any question in symplectic geometry where kind of this delicate difference would be important somehow. Okay, so sorry about that. Here we go. Okay, so that's the theorem, and a few remarks. So first, the rhombic dodecahedron has a nice description. It is the dual or the polar of the difference body of the simplex. So you take the simplex, Minkowski sum with minus the simplex, and then you take the dual. This is the rhombic dodecahedron. And the second remark is that in dimension 2, the rhombic dodecahedron is the same as the permutahedron, which is just the hexagon. So we can, there is this coincidence that in dimension 2, these are the same objects. But in higher dimensions, of course, they are very different. Okay. So this is essentially the main result. And now I still need to go to the 3 other objects that appeared at the beginning of my talk and explain how they are related to this theorem. Okay. Yes, and sorry, and this is maybe another remark that, okay, maybe more relevant to the symplectic people, that we can actually use the methods that we developed to prove this theorem also to describe symplectic images of ellipsoids and symplectic images of the polydisk. So this is kind of a natural adaptation of the same tools that we need for the proof of the main results. So if you think about the 2-dimensional case, then the ball is just an hexagon, and you can somehow deform the hexagon to get this family of ellipsoids. Okay. So I'm turning now to the second object that appeared at the beginning of my talk, and this is the notion of Minkowski billiards. So let me recall the kind of the general setting. So we consider the classical phase space. We have a smooth, let's say, smooth compact hypersurface. And then we have the usual characteristic flow along the boundary of this domain. Now, if you think about, one way, or one nice way to think about this is that you can start with any Riemannian manifold, and there is, of course, a natural correspondence between the characteristic flow in the cotangent space and the geodesic flow here on X. And there is another kind of, I would say, ideology that if you have, let's say, a surface and some kind of geodesic flow on the surface, and you squeeze kind of the surface to make it flat, then in the limit case, okay, so I'm not sure how to draw it exactly, you get something which is completely flat, and the geodesic flow will converge to just billiard dynamics. Okay, so this is something that it's not very a precise mathematical statement, but this is something that one can imagine, right? You have a surface with some geodesics, you kind of turn it into a flat object, and then the geodesics become kind of billiard orbits. Okay. So at least on the kind of the level of intuition, there is a natural relation between these closed characteristics on the cotangent space and billiard dynamics via this procedure, right? So closed characteristics, geodesics here, geodesics, and billiard trajectories. Okay. And this can be made into a precise mathematical statement. And I'm sure that this was known to experts in the field, but together with Chiriart, Avidan, we wrote down the details. So what is the statement? Consider the the characteristic foliation, the Rib dynamics, on the boundary of such a Lagrangian product. Okay, so now two important remarks. I'm not taking any smooth domain. I'm taking really a Lagrangian product, so it's definitely not going to be smooth, right? It's a product configuration. And of course, it's very special. It has this Lagrangian product built in the domain. And there are, of course, issues about, okay, what do you mean Reb dynamics when it is not smooth, right? How you define the dynamics when you don't have smoothness. Okay, the short answer, there is kind of a long, precise answer to this question, but the short answer is that what comes to the rescue is convexity, right? So roughly speaking, all convex functions are differentiable in some sense, right? So you need to replace the kind of the derivative with the subgradient. There are some standard ways that you can still do analysis on non-regular objects as long as they are convex. Okay? So Reb dynamics on convex, non-smooth hypersurfaces still makes perfect sense. And the statement is that if you start with such, maybe I can show you a picture, if you start with such a product configuration and you consider the Reb dynamics up here, right, then essentially along this procedure, what you see when you look downstairs here is a billiard type dynamics. But it's not the usual Euclidean billiards, because you can think about this configuration as, again, K plays the role of the billiard table in the Q space. And on every fiber, you don't have a Euclidean ball. You have a certain convex domain, right? So this convex domain controls the geometry. This is the Minkowski norm that you have on every fiber. So the projection is not going to be the usual Euclidean billiards, but Minkowski billiards. So the reflection law is not going to be the Euclidean one. In other words, if you would, instead of k times t, if you would start with k times b, where b is the Euclidean ball, then it would be just the usual billiards that we see more or less in this particular picture. Does this make sense? This is a good time to stop and see if there are questions.
So it's like a Finsler geodesic flow.
It is, exactly. It is a Finsler geodesic flow, but kind of a special case because it's the same convex domain in every fiber. I mean, the Finsler situation, you can have like, different convex domains in different fibers. This is really the same one. So it's a special case of a Finsler geodesic flow. Okay. Any other questions?
The trajectory, so inside this billiard, so the trajectories are straight lines, right?
Yes.
And the only difference is the angles. The more.
Yes, exactly. So I can try to explain the dynamics. Okay. So it's something like this. So if you kind of really write down the equation for the Reb dynamics, it's something like this. You start with the point on the boundary, and a generic point would be, say, in the interior here and on the boundary here. Okay? Sorry, here. And then what you're supposed to do is kind of follow or keep on moving from this point in this particular direction till you hit the boundary. And then when you hit the boundary here, you have to take the outer normal. Okay, let's say. Okay, this is a very bad drawing, but at least conceptually. You have to take the outer normal at this point, and now you start to move, and this is just the equation of the Reb dynamics. You start to move in minus this direction till you hit a different point here. Now, why minus? Because we use the symplectic form, so there is like minus in one of the coordinates. And when you hit this point, then again, you take the outer normal at this point, and you continue to move in this particular direction. Let me maybe use a different color. Okay, so this is the reflection law. And if this was the Euclidean ball, one can check by simple geometry that this would be the standard reflection law that we know from Euclidean billiard dynamics.
And this convex body on the right-hand side is smooth, right?
That's a good question. So for now, let's say just to have this picture in mind for kind of the first approximation, you can assume that this is smooth. But if it is not smooth, then essentially you can do the same thing. So let's consider a case where you have, let's say, here something smooth and a geometry that looks like this, right? Kind of a non-smooth example. So what's going to happen here is that you have these normals on these parts of T, and if you hit the corner, so then you have the whole family of kind of outer normals at this point. So in a sense, the billiard dynamics or the Reb flow is not well defined. I mean, you can always find, how should I say it? The corresponding Hamiltonian equation always has a solution, but it's not going to be unique. So kind of from the billiard point of view, you might have different ways. I mean, all these normals would give you different ways to move inside the domain T. Okay. But the same kind of dynamics that I described here would hold also in the non-smooth case. And in fact, in the examples, of course, that I'm going to use, like this rhombic dodecahedron and so forth, they are non-smooth. Thank you. Other questions about this? OK. So that's Minkowski billiards. And now we have the rhombic dodecahedron. We have Minkowski billiards. Oh, and of course, we started with a long discussion about symplectic balls, but we still don't have the Toda lattice. So let me slowly explain how the Toda lattice enters the picture. OK. OK, so kind of as a motivating question, let's kind of refine the original question that we started with. And instead of asking more kind of in general what could be said about the symplectic image of the ball, let's focus on this kind of special case. Let's take Lagrangian product configurations. And moreover, we are going to assume that one of them is just the simplex. Okay, so it's a very special case. And then the other one is any convex domain. And ask, what about this particular configuration? Okay, so it's kind of a sub-question of the original one. We take only Lagrangian products and not general Lagrangian product, but we force one of the domains. You can think about this as the billiard table. So the billiard table is the simplex. Okay, we take the simplex with some geometry, and we want to know when this configuration is a symplectic ball. Okay. So one possible way to approach this question is to try to use a beautiful result by Alberto, Barney, Umberto, and Pedro. But note that for this result, you need to have something, a convex domain, which is smooth. And so the assumptions are smooth and strict convexity. But at least under these assumptions, if you have a configuration which is smooth and strictly convex, then if it is Zoll, meaning that for every point there is a kind of a closed characteristics, and all these characteristics have the same action, that's the definition of Zoll, then this domain should be a symplectic ball. Okay? Of course, we cannot apply this theorem as is, because the configuration is definitely not smooth. Okay? But we can still try to see kind of if they use the same ideology, right? So we kind of change the question. So we have our table, which is the simplex, so just a triangle, equilateral triangle. And now we ask, OK, can you come up with a geometry? Remember, the other domain here, oh, sorry, yes, this T is basically a choice of a geometry, right? So we ask, can you find a geometry so that if you would play billiard dynamics with respect to this particular geometry, the billiard dynamics would be Zoll? I mean, it's easy to see that this is not the Euclidean geometry, right? I mean, the Euclidean geometry, if you just play with billiard dynamics inside the equilateral triangle, you see that there are different orbits with different lengths, different action. Okay? So do you want to guess, at least those of you who never heard this talk before, which geometry should one take? Yeah, I mean, of course, one needs to play a little bit with some trajectories to see the answer. But it's probably not surprising that one answer, this is not a unique answer, but one answer is that just take the hexagon, right? If you use the hexagon as the unit ball of a norm, and you use this norm to define the reflection law inside the equilateral triangle, then you see that the dynamics inside the triangle is actually Zoll, right? So in particular, let me explain this point. So let's start with the Euclidean case. I'm really sorry about the quality of these pictures. So of course, the systole in this particular case would be this trajectory here. That's the shortest billiard trajectory. Okay? The second one is the height, or any one of the heights. Right? Now, of course, for this configuration to be Zoll, we can't have something like that. These two things should have the same length. And this is exactly what happened when you take the hexagon, right? Because the hexagon really controls the geometry, so not just the reflection law, but also the length of the trajectory. So everything, we don't have a canonical notion of length. The length is determined by this configuration here. So if you replace the Euclidean geometry with this, and everything is measured with respect to this geometry, then the length of these two orbits are exactly the same. Okay? So this is Zoll in that sense. Does this make sense? Okay. And again, I'm slightly cheating here because you actually, because of, okay, so there is this identification between the tangent space and the cotangent space. It's always a nightmare. So you have to measure everything with respect to the polar or the dual of this configuration. Okay, but the dual of the hexagon is still a hexagon, kind of. Okay, but the idea is here. Okay, so I'm kind of avoiding, or I'm trying to avoid technical details. Is this okay? Any questions about this? Okay, so good. So now we have our candidate for an answer to this question. So let's keep on in the same direction. Let's try to prove that this configuration is a symplectic ball, right? Okay, that's the next step. So you go back and you start to analyze the actual dynamics in this particular configuration. And it's easy to see. I mean, you just play with it and you think, OK, this is a completely integrable system. I mean, it's a very nice. I mean, the trajectories are extremely nice. It looks integrable. So it's kind of, I wrote in my slides, natural. But let me comment about this. So it seems natural to use integrability somehow to show that this is actually a symplectic ball. But as far as I know, the first time that this approach was kind of implemented in this type of question is a work by Vinicius, where he studied the usual Euclidean billiard inside the disk. And in that work, he used the integrability of the classical Euclidean dynamics to somehow symplectically understand how what is the kind of the symplectic way to look at this particular configuration. So it's maybe the word natural here is slightly misleading. OK, but again, one can try to use integrability. And OK, so how to do it? Well, you have to come up with the commuting Hamiltonian functions, right? If you ignore the red parts, then you can naturally start with something that looks like the usual kind of Hamiltonian for the kind of straight motions, which is right here. And then to use the particular symmetry of the triangle to come with another Hamiltonian function, right? So there is kind of a natural guess how to continue from this point, how to kind of cook two commuting Hamiltonian functions that somehow describe these or closely related to this particular dynamical system. But the problem is that, OK, you try to come up with two Hamiltonian functions, but commuting Hamiltonian functions, but this is not enough, right? What you want to do is to apply the essentially you want to find global action angle coordinates to have kind of a nice symplectic image of this configuration. Or more precisely, you need to find some nice global suitable cycles when you use the Arnold-Youville theorem. And this was really a problem for a long time, so really a technical issue that we somehow couldn't cross for a very long time, trying different ways to see if we can overcome this. And then we somehow, by some sort of luck, I would say, discovered that this was actually done before, but in a very different context. And this is how the Toda lattice entered the picture. And this is what I want to explain next. Okay? So we had almost all the ingredients, the symplectic balls, the permutahedron, which is this in dimension 2, is this hexagon here. And now the Toda lattice enters the story. And I want to explain a little bit more about this connection. So let me, again, go slightly back and be more precise about what's going on. So the goal is to show that this Lagrangian product, regular simplex, and OK, I wrote here symmetric region, but just please ignore the symmetric region here and just think about the rhombic dodecahedron. Then this configuration is symplectomorphic to a nice toric domain. So this is the way that we use integrability. If we know that this system is integrable, then we can use the Arnold-Youville theorem to find global action angle coordinates and to have a nice description of this particular configuration. So what are the main ideas in the proof? And again, at this point, I guess I'm taking a little risk, because if you are familiar with the paper, then what I'm going to say next is actually not what's actually going on in the paper. But I somehow wanted to explain the ideology, and it is slightly different with what we actually did in the proof of this theorem. So the first idea, this is something that I already mentioned, is that the Reb flow of this particular or any Lagrangian configuration, Lagrangian product configuration, corresponds to billiar dynamic, right? K is the billiar table, T is the geometry. Okay, we saw this part already. The second part, or the second idea in the proof, is that billiard dynamics in the simplex, or billiard dynamics in a triangle, has a very nice physical model. It corresponds to the motion of, or to the elastic collisions of particles on a finite ring. So this is actually, and you can see here kind of the picture. Of course, the masses of the particle affect the actual size of the triangle. But this is something which is very simple, and for some reason, I think that the first paper on this is maybe 1995 or 1997. So it's kind of very recent, although the connection is very natural. This is way after the Toda lattice paper, of course. Yes. So again, the second idea that goes into the proof is that billiard in the simplex, one can translate the dynamics of billiard in the simplex to a different dynamical system. These motions, these particles going along the ring with kind of a perfect elastic collision between them. And from here, you are almost at the Toda lattice. So such systems of collisions are exactly the dynamical system that was studied by Toda, and this is the actual model of, or this is one of the models of the Toda lattice dynamical system. Okay. So now we have all the ingredients, right? So we started with symplectic balls. We went through these special Lagrangian product configurations. We restricted ourselves to a very special case where one of these domains is the simplex. The reason for that, in a sense, is because of this. Okay? So billiards in the simplex is kind of are special from kind of this dynamical point of view. And this was, this system was studied extensively. In particular, we have this connection to the Toda lattice system. Okay, and okay, there are a lot of slightly technical details here, but roughly speaking, it's not the actual Toda lattice system that we need to use, but some sort of a deformation of the Toda lattice model So you see this parameter e to the minus c here, and kind of going to the limit, if you kind of take c to the limit, then this is just the part of the Hamiltonian which controls the straight motion inside the domain. And on the boundary, you have this infinite potential, which is exactly along the boundary of the simplex. So I'm not very precise here, but roughly speaking, billiard in an equilateral triangle can be obtained in some limiting procedure from these kind of Toda lattice model via this limiting procedure. Okay, so I'm sorry that I'm not giving more details about this. So let me go maybe, not here, I want to go back actually. So I want to have this on the board. Yes, sorry, there were.
One integral of motion, of course, is square length, right?
Yes, yes.
One more.
Well, it's not. Yes, so I mean, it's slightly more tricky than that because having two commuting Hamiltonian functions, I mean, for the purpose of what we want really to show that this configuration is symplectomorphic to what we call a toric domain. So just finding two commuting Hamiltonians is somehow not enough. You can use the Arnold-Liouville theorem, but somehow locally in some sense. And you want to kind of find this global change of coordinates that would give you a nice full toric image. Yes. So this is part of these technical difficulties that I mentioned before. I mean, you can definitely come up with kind of two commuting Hamiltonians. But to actually show that you can use this Hamiltonian to come up with good global action angle coordinates, you have to work more, and we couldn't do it. I mean, we tried to take this approach, and we couldn't. But luckily for us, somehow the connection with the Toda lattice give us exactly what we want. Any questions about kind of the general idea of the proof? I'm not done yet, but I just want to stop here and see if there are any questions. Okay. Okay, so the next part is really technical. I'm probably going to skip much of the slides here. But the idea is that, okay, the Toda lattice via some clever change of coordinates is known to be completely integrable, and one can use these kind of lax pair formalism to come up with global action coordinates. So I'm definitely not going to into the details of this, but kind of what we actually discovered is that we have this black box that comes from the Toda lattice with these action angle coordinates that we can implement in our setting. So we can just, we still need this deformation and to adjust them, but in a sense, it was already made for us, these global action angle coordinates. And there are some formulas that I really don't want to, I'm not sure if, I'm going too fast, sorry. Yes, there are some formulas due to Flaschke and McLaughlin and Moser, just explicit formulas based on the spectrum for these action angle coordinates. But I really want to kind of not to go into details here because it's really quite technical, but here is kind of the actual theorem that we proved. So, and please only consider the last line here for now, okay? So here is the statement. If you take a domain which we call balanced, but balanced, just think about it, it is symmetric enough, okay? It has, in a sense, the same symmetry as the simplex and maybe slightly more than that. But anyway, a nice symmetric domain, like the rhombic dodecahedron is a good example of such a balanced configuration. What we actually proved is that any such symmetric enough configuration, the Lagrangian product of the simplex and this configuration is going to be symplectomorphic to a certain toric domain, which we can completely describe using a certain function. And as soon as we have something like that, we can kind of do the reverse engineering and say, OK, we know how to translate this configuration A times the simplex into a toric domain via something, OK, let's call it rho. Then you can go backward and say, well, this is the ball. I mean, this is the toric image of the ball. Let's go backward and see what is this A that appear in the last line of this slide. And this balanced convex domain A turned out to be the rhombic dodecahedron. So it's kind of by chance that we kind of aim to show that the simplex times the permutahedron is symplectomorphic to a ball. But using this idea and this machinery, what we discovered is that if we do the reverse engineering and find out what is this configuration A, then it is not the permutahedron, but the rhombic dodecahedron. So that's the proof of the statement. And of course, there are two. Do I have like a few more minutes? 3, 4 more minutes? So I should say that there are kind of natural questions, kind of more or less going in the same direction. So if you are familiar with the Toda lattice, then you know that there are some natural extensions of the classical Toda lattice with other root systems. So the one that I show you on the slide, it is the Toda lattice associated with the AN, so-called AN root systems. So one can, of course, try to check what will happen if we use different models of the Toda lattice. Can we end up with different configurations, not the rhombic dodecahedron, but maybe something else, hopefully the permutahedron? So this is, of course, a very natural question. And another question has to do with these nice 5 polytopes. I think they are known as Fedorov polyhedra. They have different names. So we conjecture that if you take the simplex times any one of these 5 domains, then you should end up with something which is a symplectic ball. So this is the rhombic dodecahedron here. That's the permutahedron here. And I should say that these 5 polytopes are somehow special. They are the only polytopes that can tessellate the 3-dimensional space just by translation. So these 5 polytopes. So the kind of a natural open questions that we have in this particular direction is the first one I mentioned before. So can one use different root systems of different type of Toda-like dynamical systems to come with other examples of symplectic balls or toric domains? And yes, of course, one can also ask what would be the higher dimensional analog of these 5 polytopes, but this is already a different story. So I think I will stop at this point. Thank you very much.